Hello everyone, this is another STAAD Pro Connect Edition tutorial. In this tutorial I'm going to show you how to perform a time history analysis using a specific ground motion. For the ground motion, I will use Kobe earthquake ground motion. You can find this earthquake records from the strong database ground motion, or in case if you can't, so I will provide you a link, you can download it. After that, you will copy this ground motion and you can make as a text file, and I write here a text file and just starting from 00 and then it's almost 40 seconds. You paste this text file in the same directory that you will save your model. So now we are back here and we want to give some information about the model. So the model is a 3-bay, 4 meters length, and it's a 10-story structure, which each story has 3 meters. So we will use a concrete moment frame structure, and the column size is 40 by 40, which we were considering a uniform from first floor to top floor, and a beam of 30 by 50, and as well as we will have a as concrete slab for centimeters, 50 centimeters. So the concrete materials we were considering concrete of 30 megapascal. So the loading is we have dynamic load, ground motion, and we also have a self load of the structure, and also 2 kilonewton per square meters as a dead load. So we jump to that software called TimeHistory Analysis. So I can using metric and analytic mode. So for the sample stages I create from the wizard, structure wizard, and I can come back to the frame model and create this one. So 4 meters, 12 divided by 4 meters, and it's 15, so we have 10 stories that we cause 30 meters and 10 stories. This is also the same, and okay. So now the model is created and we go to the properties. First we want to define some section, so the section is called rectangular concrete. So the first one is 0.4 for the column and 0.4 for the column called at, and the second one is, which is YD, the height of the column, 15, and this is 30. Now we want to assign, but before that let me define the thickness also for the slab, 0.15 at. Here is going to the select and using beam, and going to select first column, and here is parallel to Y, and assign to selected beam, and here is, so again comes to the beam and select X, select Z, assign again. In the same time the beam is selected, we come to the geometry, and from here called infill plates. So we created plates. Now let's go to that plate, and again in the select menus we come to here, we're gonna call the plate, all plate is selected, and we're gonna assign, and here is assign. If you go to see in a 3D rendering, and this is the structure. So in this case I'm going to delete the 9 stories metal slabs. I'm gonna just delete this one or 3 because I want to create an opening to the structure. So you can right click here and just cursor to should be as a plate. Now I can select this entire 1, 2, 3. You can see the entire slab is selected. I can create a new view from the selected, and now you can see here. So I can go to one of the dimension again in one of the views. Let me come to this one. I want to delete this one. So again, select this one, and I'm going to top, and you can select. So I'm gonna delete this. Just press the delete, or you can go to new view, and you can see the active. Now, and just press the delete, and it will be deleted. Now we comes to the back to the view, display the whole structure, and you can see here. If I go to 3D views, and you can see here is the entire structure. So we can also fill the last one, this one, and for this I can go to top view and selecting the last floor slab. Let me I can go to the select, and the plate, I can select actually, or we can redraw again, or just we can go back to undo and see. So now you can see the entire strap. You can see here. So except the last floor, the other part is deleted. So I'm gonna back one more, and you can see again. Now I go back rendering, and just the last floor slab is exists, and the other is deleted. Now we finished here. We go to the materials, though we should change that concrete to concrete 30. So we can comes to here, create a new concrete. Manually we also can give, and also we can okay, in concrete we can go to edit, and this is 27,000, so we want to make it 30,000. 30,000, the unit is different. 30,000 kilonewton per square meters. So we change the compressive strength of the concrete, and now we go to the support, and let's go to the front view here, and creating the support. Let's be fixed in the bottom, and assigning to the cursor selected node. Now we are in a 3D mode. Then we can see the structure with boundary condition. Now the important part is that loading part, because we want to apply dynamic load as a ground motion and also as dead load. So we have two methods that we can provide. The first, we can define the time history. Let's add time history, and we want to give the integration time step is 0.1. If you come here and check, this one is 0. Between these 2 points is 0.01 second. So we give 0.1 second, and this is the loading type is acceleration, and we want the program should read the file from giving name. I can come to here and I can say rename. So I'm gonna give the name of this text with the type of the file, so the text file. So I have to give this one. It's called Kubi text. So we don't have anything else, and it's called add. And the second, we have to define some pattern. so the time step is already defined, and here is the damping. So how much damping you want to consider for this time history or for the analysis. So for the concrete structure is usually 5%, but you can play with this damping, critical damping, and see how the structure responds. So let's be 5 is okay, and the time arrival is 0, and so that's it. Okay, and we finished the time history, damping, and everything. Now here is we have I already said that there are two options that you can define. One is the reference load, that you will define the gravity load, and in the next you do need to create a load case, or you ignore the load and the reference load case here, and you come to a load case and define the same load as a seismic load to the H direction. So I'm going to use this method. So I'm going to let's use gravity load. So that gravity load is the structure self load. I'm called gravity load, and the second load is called a dynamic load. Loads. So in the gravity load, I want to add self load of the structure in one direction in here, called add, and the second is a floor load also exists. So the total structure height is 30 meters, and it's a negative of -2 kilonewton per square meters. So I'm going to call that. Now you can see this load is added, and also I want to add this one assigned to view. Now after the first gravity load is applied, now in the dynamic load we will apply the same loads in swivel direction. So we called add. So this is the gravity load, and this should be x. You can remove the minus factors, it's not important. We call 1 and 2 and 3, and again in the same we can come here and again to use that floor load in the 2 kilonewtons to the 13 in the global x, in the global y, in the global z. So now you can see the load is applied in multiple directions. So I'm gonna apply it to the view now. Apply or assign to view. Assign to view. Assign to view. Now the last one is we wanna add in the same load a time history. So we select that there, and we come to the time history, and we want to use the previous defined arrival time 0, and it's the ground motion, so it should be acceleration, and you can apply in multiple direction and also in single direction. So I assume just one direction x because it's a typical structure. The response may be quite similar, and this is the factor that the unit is J, and we are using kilonewton meters, so we wanna times by 9.81, and so now we are almost done. So the loading is completed. In case if we want to create the combination or something else, or we want to design based on this dynamic analysis, we can create some combination. So in this tutorial we're not considering the design part, so just we were going to see how the structure with these properties will respond under the earthquake. And we go to the analysis part, and we also can define some miscellaneous command or cutoff mode shape. So let's be 20, and okay, and we're gonna call the command to perform analysis called add, and the last one we press the analysis. So the program wanna save it, and we can wait to program solve. Now here is the analysis, and the analysis completed, so there is no error warning. We can go directly to the post processing. We can apply, okay, and you can select based on this dynamic load, and the displacement is here, and this is the displacement in this node. So we can go to the layout here, and first let's see the mode shape of the structure. So the first mode is here. In case if we want to increase the scaling, and we can come to the scale, and for the scaling let's see the result, and this is the bending, and I want to see this is the animation actually. Okay, give me the scale, and here I want to see the displacement. So in the displacement, let's be 1, apply, and or maybe this is gonna be 10. Some changes made, or animation, we can say deflection, or we can create some animation. Let's see mode. We're gonna call it mode, and deflection, or mode shape. Yes, now the animation is begin, and this is the first mode. We can apply. Let's go to the mode 2, and you can see here, if we increase the scale, but we should stop first. Let's go to mode 10. So here is some degradation, some movement. I'm gonna stop this one, and we come back to here. We're gonna see the displacement. Now here is the response of this node in the displacement. So the displacement is maximum displacement is 141 millimeter. So, and this is the node 44. In y-axis is 3.4. So this direction is top direction, and z direction is also small, but quite a large displacement is observed in the x, because we applied the earthquakes in the x direction. So we also can measure it in the bottom, and you can see first floor, second floor, and the program automatically give you the top nodes, the maximum displacement, and you also can see first floor, second floor, and we can go to the acceleration, and here is the acceleration, and it's using meter per square second, and here is the maximum minus 2.5, so it's quite large. Here is 6.5 meters. Okay, now we also can see some beam column response, so beam results, and this is quite large. If I go to the scale, and the scale should be apply, so it's very large. We can change it, this one, let's in the result, and we want to give 1, so apply, and I'm gonna call 1, so I'm using 1. So you can actually you can now you can see the moment in y, moment in z is quite large, and other direction, and the force in fx, so deflection, everything like this. So you can interpret the results as you wish, and there is also some utility. You can see the node tools and everything, some analysis output, and like this you can see the response of this structure, and also you can change. Let me go back to the result, and this is the let's go to time steps, and I'm going to show you in the 15 second, and you can see the deformation is like this. And you also can animate the deflection and apply, and you can see it in this time steps. If I increase this one to, so exactly this one is okay, you can see the deformation. And as well as you can go back to the analytical model and go to the loading, and comes to here, and in the ground motion here you create one more. So let's say add load, and you come to the time history, and this time using the same acceleration, but this time use Z, so this direction. So the amplitude is 9.81. So we're gonna add, so yes, we have created two directions, and now we can see the response again. And you go back to the analysis, and we want to run, and the program will start to run. So this time we applied in multi-directional. So I'm gonna go to post processing and call it okay, and this is 0, and you can go to some this direction. You can see here it's quite different. It's become, the effect is quite large, and you can see the response, the displacement, rotational, everything. And you also go back to the layout and see the displacement. Now the displacement is in the x-axis, is 30.1, and in the second one, which is y, which is vertical, is, but in x, y is equal, which I already discussed about the typical of the structure, that the structure is typical, so the displacement will be actually the same in the both directions. So it's here in the z direction, this one, in y direction is that. So we selected this node. If we select this one, you can see it here, 141, 141, and the y direction is also changed. So this is the end of the tutorial. If you have any question, please put in the comment, and we'll find time to answer you. And for more tutorial, please like, comment, or subscribe to the channel. See you next time.